Hey everyone, in this video we're going to talk about divergence, curl, and conservative vector fields and kind of the relationship between some of these terms here. So just to kind of recap a little bit, a vector field f x, y, z takes in this point x, y, z and gives you a vector back. So it that's not a vector. So it might take first component is some function of x, y, and z. Second component is another function of x, y, and z. And then our third component is another one. Okay, so sorry, I get a little cramped there at the end. These are not exponents. They're just subs or superscripts, so that way we can tell apart our different components here. And this is a vector field. And I mean, vector fields can have only 2 dimensions as well. I've just chosen to show a 3-dimensional one here. So, but yeah, you can have as many components here as you want. So anyway, just to kind of give you a quick example of what some of these could look like, f of x, y, z equal to x cubed y, and then z plus 2xy sine of x is a vector field because it takes in this point and then returns a vector like so. And then another one would be something kind of like this, possibly. They can really look like anything, to be honest. But y, z, e to the x, y, z. X, z, e to the x, y, z. And then x, y, e to the x, y, z. Okay, so connected to vector fields, we have a few different terms. So the first one that we're going to look at is going to be something called, the divergence of a vector field. And this is denoted, just a little div here in front of our vector field f. And you compute this by taking this kind of gradient operator dotted with f. And so what does this guy look like right here? Well, this is just the vector partial. This tells us to take the partial. We haven't taken any partials yet. With respect to x, partial with respect to y, partial with respect to z. And then we dot that with f1, f2, and f3. So just, f right there. So what you get then is the sum of partial with respect to x of f1 plus partial with respect to y of f2, and then plus partial with respect to z of f3, just like so. So yeah, that is divergence. So just like maybe an example of computing it, if we wanted to find the divergence of our vector field f that we had up here, this is equal to partial with respect to x of x cubed y plus partial with respect to y of z plus 2xy, and then plus partial with respect to z of sine of x. Okay, so again, emphasizing that we have not taken any partial derivatives yet with these little guys right here, but they tell us to take the partial derivatives when they've been kind of multiplied there. So right here we get 3x squared y plus this z is going to go away, and then 2x, and then partial with respect to z of sine of, that is an x there, that's just going to be 0. So yeah, that's pretty much all there is to taking the divergence. We do have kind of, I guess, a fancy word that goes alongside the divergence. So if the divergence winds up happening to be equal to 0, then we say that f is incompressible. So a lot of times you'll find in math that when we apply some sort of operation to something, we get 0 back, we give it a name. In the case of the divergence, we say that it is incompressible. So yeah, so that is divergence. The next big idea that goes with vector fields is the notion of curl, which kind of gives you an idea of how much rotation is in your vector field. So the curl of f is defined to be that same gradient operator crossed with f this time. So you're looking at more of this cross product determinant type thing. So you have I hat, j hat, k hat with those partial operators or partial derivatives in here, and then with the components from f as well, just like so. So for example, if we wanted to look at the curl of f, where this is, again, the same f from what we wrote earlier, we're going to be looking at the determinants I hat, j hat, k hat of the partial with respect to x, partial with respect to y, partial with respect to z, and then we have x cubed y, z plus 2xy, and then sine of x. So that gives you I hat times partial of y with partial with respect to y of sine x minus partial with respect to z of z plus 2xy, and then minus j hats partial with respect to x of sine of x, and then minus partial with respect to z of x cubed y, and then plus k hats times or k hats partial with respect to x of, now we're looking at this piece right here, z plus 2xy, and then minus partial with respect to y of x cubed y. Okay, great. So this is all, we just got to take all these partial derivatives. We get I hats times, that's going to be 0 minus, that's just going to give me 1. And then minus j hat times, that's going to give me cosine of x, and then that's just going to be a 0. And then I have k hats, that's going to give me 2y minus, looks like x cubed. So I guess if I wanted to write this a little bit differently, I'm going to get negative 1 negative cosine of x, and then 2y minus x cubed is that curl right there. So yeah, that's how you compute curl. You just take that cross product right there. And I guess one thing to kind of note is that this is pretty parallel to this idea of divergence. We have this little gradient operator thing right here, and we have something for the dot product. So dot product, divergence, they both start with D, and then cross product and curl both start with C. So same two pieces, just a different operation there. So, okay. Now, like I said earlier, when things are equal to 0, we like to give them a fancy name. So in this particular instance, if the curl of f is equal to the 0 vector, then we say that f is irrotational, which really just means that it doesn't have any rotation in it. I mean, it's exactly what it sounds like. Cool. All right, so there's one more big idea that comes in with vector fields, and this is the idea of a vector field being conservative. So we say that f is a conservative vector field if, and this is one of the really nice things about these, is that if there exists some function f called the potential function, such that the gradient of f is what produced our vector field. So the little function f, not the gradient, just the little function, is called the potential function. So just this piece right here. And then that gives us a vector field. So anytime that we can trace a vector field back to some function, we call it conservative. Now, not every single vector field can possibly be traced back to a function like this. So sometimes you're not able to reconstruct that function. But Sometimes you can't, and it gives us some really nice properties. So how do we check to make sure that a vector field is conservative? There's a couple of options here. If f is a 2D, then that just means that f can be written as f1, f2, like that. Then we check that the partial derivative with respect to y for my first component is the same as the partial derivative with respect to x for the second component. And in the 3D case, if f is 3D, so I just mean that f has 3 components. So like our 2 examples earlier. What we're going to check is that the curl of f, which is equal to that gradient thing crossed with f, that has to be equal to 0. So more specifically then, we want for f to be irrotational. Okay. So just kind of looking at that, some of these ideas are connected. Okay. Let's look at an example of this. So if I look at our first one, f equal to x cubed y, z plus 2xy, and then a sine of x, this is not conservative, since we had found earlier that the curl was equal to -1 negative cosine of x, and then the 2y plus x cubed, I think. And that is not equal to 0. That doesn't give us the 0 vector back. So this is not a conservative vector field. However, our other example that we had earlier, g equal to yz e to the xyz, xz e to the xyz, and then xy e to the xyz is conservative. And I'll leave it to you to check the details of this, but you will find that the curl of this is indeed equal to 0. So what this means is, for this particular vector field right here, we can find a potential function. That produced it. So in particular, we can find a little g such that when we take its gradient, it gives us our vector field. And in case you're curious, this is g xyz equal to e to the xyz. And you can kind of check that. If you take the gradient of this, you're going to wind up with this guy right here. So yeah. Okay, so that kind of summarizes everything about vector fields that we've learned so far. We have this idea of the conservative vector field, which ties back into the curl. And then we also have this notion of divergence, which uses a dot product instead of a cross product. So yeah, lots of words, lots of terminology, but a lot of them are really pretty closely related and tied together. So that's pretty nice. Yeah, so that pretty much wraps up this video.